Okay, this is the third part of Chapter 8. We're going to be talking about what are called resonance structures today, and we're also going to start talking about uh, determining the formal charge on the atoms in a molecule. Okay, resonance structures. A lot of times a resonance structure just means that when you draw a molecule such as O3, so if we draw the Lewis structure for O3, the Lewis structure looks like this, where we've got an oxygen-oxygen single bond here, and we've got an oxygen-oxygen double bond here. And so your two possibilities, you could write it one way with, again, the double bond on the right and the single bond on the left. And another way you could write it is you could write it the oxygen with the double bond over here and the single bond over here. And then you would have two different structures for ozone. Okay? Anytime that you have a molecule in which two or more alternative Lewis structures can be drawn that still follow the octet rule, you have what are called resonance structures. And you separate them, you show that they're resonance structures by placing this double-headed arrow between them, where you've got the two different possibilities there with a double-headed arrow on them. Okay, so some possibilities here. NO3 minus would be N with the three O's on it. We've got a total of 5 plus 18 is 23, plus 1 is 24 electrons. So we've got 24 electrons all total. And we're out of electrons, but again, notice that nitrogen in the middle does not have 8 electrons on it, so we have to take 2 of the electrons from one of the outer atoms and put it in there. So we're going to take 2 electrons around here, put them on here. Well, that doesn't seem quite right, does it? Because that means that the oxygen would only have 6. So we can't put the 2 electrons on there, but we take the 2 electrons off of there and we make a double bond. So we've got a nitrogen-oxygen double bond. Now we could do the same thing again and make the double bond up here, and we could do it again and make the double bond down here. Okay, so, and actually all of these are pretty somewhat similar to that same structure. Okay, another common molecule is called the benzene molecule. A benzene molecule is one that has 6 carbons and 6 hydrogens, and they're arranged in a hexagonal shape like this. And then each carbon has 1 hydrogen attached to it like this. And then you've got an alternating double bond. So you've got a double bond here, 1 here, and 1 here. And then if you draw the resonance structure for that, basically this double bond moves to here, this double bond to here, and this double bond to here. So there are 2 different resonance structures for the benzene molecule. Okay, and although we can draw many different resonance structures for a particular molecule, what actually occurs is a combination of both bonds. So you've got both bonds being able to, both the single and the double bond really existing at the same time in both places. Okay, many times, for example, if we go back with ozone, a common misconception is that students think that it alternates, it switches back and forth between this and this. But what actually we find is that the bond length between these two oxygens and these 2 oxygens is exactly the same, which means there is no double bond and there is no single bond. It is a combination of both bonds. So it's as if there is 1.5 bonds in both places. And if you look in your text on page 323, they actually show 323. Sorry, they actually show an ozone molecule, and what they show is basically they've got the 3 parts here: the ozone, the oxygen here, and these 2 oxygen, and they show that these bond distances are exactly the same. I think they're like 1.278 angstroms. Okay, which means that those bonds are exactly the same, which means this doesn't really exist and this doesn't really exist. What really exists is you've got, like I said, like a bond and a half here and a bond and a half here between both of them. And yeah, that doesn't really make sense, and then we can't really draw a Lewis structure that appropriately shows that. We would never draw it like that. And so that's why we have to draw the resonance structures, is because those are the only 2 ways using electrons as matter as actually working correctly. Okay, but that is an important thing to be able to do, is to be able to differentiate, why are the bonds in ozone different from the, from the bonds in like CO2 or something like that, because it has two double bonds, where this has got like 1.5 bonds in both places. Okay, and then the last thing is just formal charges. Formal charges is a way, and this is not very commonly seen on the AP exam, but there is one question in your review packet about it. When drawing Lewis structures, we show how the electrons are distributed in a molecule. But many times with like resonance structures, an atom can be written different ways while still following the octet rule. So there is another way to determine whether it's the correct way to draw it, and that is using the formal charge. Okay. The formal charge is the charge an atom, a molecule would have if all the atoms had the same electronegativity. Okay, and we'll talk about that here in just a little bit. So, first of all, how do you calculate formal charge? First of all, let's look at, let me give you two different molecules. Let me give you the sulfate ion. Sulfate is SO4 2-. So one way of drawing it, obeying the octet rule, is like this. It's got 32 electrons. Another way of drawing it is like this. This does not obey the octet rule, but we're going to see something here in just a second. Should be a double bond. So two different structures. Now, the first one, like I said, follows the octet rule. This one here follows the octet rule. The one on the right does not. Okay, but basically, here's what we're going to do. We're going to calculate the formal charge. And when we calculate the formal charge, we go atom by atom through the molecule, and we calculate what charge it has on it. For example, oxygen, if you look at the periodic table, oxygen normally has 6 valence electrons. So that's what we start with. Okay? So it's the number of valence electrons in the isolated atom using the periodic table. So oxygen normally has 6, minus the dots on it. So 1, 2, 3, 4, 5, 6, plus each bond counts as 1. So that's a minus 7. So each dot counts as 1 and each bond counts as 1. That's a minus 1 charge. Well, each oxygen is the same. 6, and then again 2, 4, 6, 7 for the bond, negative 1. So each of these oxygens is going to have a formal charge of negative 1. Sulfur, on the other hand, is in the same group as carbon, so it again still has 6 valence electrons normally, minus 1, 2, 3, 4, and no dots on it, so it has a formal charge of plus 2. So in this molecule, each oxygen is minus 1 for a total of minus 4, and the sulfur is plus 2, making it negative 2 all total. However, in this molecule over here with the double bonds, we find that this oxygen here and this oxygen here are both going to be 0. Okay, 1, 2, 3, 4, 5, 6. 6 minus 6, 0. These oxygens here are still going to be the negative 1 ones, just like on the other molecule. But then the sulfur also is going to be 6 minus 1, 2, 3, 4, 5, 6. So the only formal charges we see on this one are right here and right here. So the molecule on the left, we've got a ton of formal charges. The molecule on the right, we have a lot less formal charges. Which one's the right one? The structure with the least amount of formal charges is the molecule most likely to actually exist. So what they would do on the exam is they would give you those two structures for sulfate, and they would say, yeah, using principles of atomic structure, blah, 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 which of the following best describes the sulfate molecule? And then they would have to say, justify your answer in terms of formal charge. Because if we just follow the octet rule, the one on the left is better because it does follow the octet rule. The one on the right, though, in terms of formal charge, is the better one because it has fewer formal charges on the molecule. Well, how do you know which one to do, formal charge or octet rule? If they say draw the Lewis structure, don't worry about formal charges at all. I've only seen one question ever on formal charge. but so it could certainly be on there, and it was just 3 or 4 years ago. So it's certainly something that could be on the exam. Just be aware of that. But they would have to specifically say, justify your answer in terms of formal charge. Then you would say the molecule on the right best represents the molecule because the other molecule has formal charge on every atom, whereas on this one on the right it only has it on 2. Okay, so here's some different ones here. So if we do CO2, one way of drawing that is like this. Another way of drawing it is like this, with a single and a triple bond. And this one, actually, you do see that it still does obey the octet rule. Everything still has 8. But here we've got a formal charge of 0, 0, and 0. Here we're going to have a formal charge of 6 minus 1, 2, 3, 4, 5, 6, 7 equals negative 1. So this is negative 1. The carbon's 0, but this oxygen is going to be positive 1. 6 minus 1, 2, 3, 4, 5. Positive 1. So here we've got no formal charges. Here we do have formal charges. That one does not best represent the molecule, and that's why when we draw CO2, we always draw 2 double bonds instead of a triple and a single. Okay, this is actually on your review packet. I believe it's question 3 of your review packet. Look at the 2 different structures. Again, this is the only time I've ever seen them use that term formal charge on the exam. So look at that and try to figure out which one would be the best representation of the molecule. There's your homework. We'll talk about it tomorrow.